Total internal reflection. Here we have a semicircular glass block. A ray of light is going to pass through the glass block as shown here. So this is the incident ray, this is the refracted ray. The ray has been refracted due to the change of speed as it leaves the glass block. There is no bending at this point as the ray meets this face at 90 degrees. That means we can concentrate on this region where the light is going from an optically dense medium to an optically less dense medium, from glass to air. The ray of light is speeding up as it comes from here to here. If we mark on the normal at 90 degrees to this face, we can then label this angle theta, the angle of incidence. So, when light travels to a less optically dense substance, it will speed up and refract away from the normal. We've now increased the angle of incidence such that the angle of refraction is now 90 degrees. We call this angle of incidence the critical angle, and this is the angle at which the angle of refraction is 90 degrees. So we can label this theta c, the critical angle. Now the angle of incidence has been increased beyond the critical angle, and all the light now reflects at this glass to air boundary. So we now have a reflected ray. So when the angle of incidence theta is greater than the critical angle, we say total internal reflection occurs. In symbols now, theta is greater than theta c, the critical angle. Now to look at the critical angle mathematically. We know from Snell's law that n1 sine theta 1 is equal to n2 sine theta 2. This is the refractive index of the substance the light starts in, times the angle of incidence with the boundary, is equal to the refractive index of the substance the light is travelling into, times the angle of refraction. In the case of the critical angle, several of these quantities take particular values. Theta 1 is the critical angle, that's our angle of incidence. Theta 2 is 90 degrees. That's the definition of the critical angle, is where the angle of refraction is 90 degrees. And the sine of 90 degrees is 1. That means this term here, sine theta 2, will just become 1. We can now simplify that expression to n1 sine of the critical angle is equal to n2, which we can rearrange to give sine of the critical angle is equal to n2 over n1, or the refractive index of the substance the light is travelling into, the faster substance, divided by the refractive index of the substance the light starts off in, the slower medium. Finally, for the special case where the light is travelling from a certain substance into air, for instance glass into air. If substance 2 is air, that means n2, the refractive index, is equal to 1. n1 we can now just call ns, the refractive index of the substance under investigation, and then this simplifies to ns sine of the critical angle is equal to 1, which we can rearrange to give sine of the critical angle is equal to 1 over the refractive index of the substance the light is leaving to enter air.